back. Recently, we concluded our discussion on the structure of atoms and molecules. By now, we should be experts at determining how and why atoms bond to form new materials and appreciate just how widely varied these materials can be. Today, we're going to take a big step forward in the course. During this lecture, we'll begin to consider not just how some of those atoms and molecules can change and react with one another, but also how they can create, consume, and even transport possibly the most precious commodity in the universe, energy. We need to understand chemical energy because just like physical energy, it can be used to predict which processes will and will not happen in nature. Chemical energy is often stored, transported, and produced to help power the many devices that we rely on every day. Chemical energy flows and is carried by every material on Earth. Plants harness it to create food for themselves through photosynthesis, taking energy from the sun and packaging it in the form of sugar molecules, which it later can tap for energy when needed. You and I harness it also when we consume food. Our bodies break down molecules of sugars, fats, and proteins and gain energy needed to keep us alive. The key to understanding the transfer and transformation of energy in chemical world lies in three very simple rules, which set the stage for a field of study known as thermodynamics. Our discussion today is going to center around the first of these so-called laws of thermodynamics. The first law of thermodynamics can be most simply stated as energy can neither be created nor destroyed. So at a glance, it sounds like energy is pretty boring stuff. You can't create it, and you can't destroy it. So exactly what can you do with it? Actually, quite a bit. Energy cannot be created or destroyed, but it can be transferred from one sample of matter to another, from a system to its surroundings. A furnace heats your home. An engine produces thrust by burning fuel. Or a battery delivers electrical power as a chemical reaction takes place inside. All of these are examples of chemical energy that we rely on every day. So, where does chemistry enter the equation? Well, remember that a chemical bond is a confinement of atoms in space which lowers the energy of that system. So, forming bonds releases energy, and breaking them requires that we put energy in. But we just said that the first law of thermodynamics tells us that we cannot simply dismiss the energy balance of a process. That chemical energy has to go somewhere when a bond is formed, and it has to come from somewhere when a bond is broken. In this way, chemical bonds act as a storage medium for energy. Chemical energy is always present, but it is also always changing and flowing as chemical processes take place. Think back to the last time you built a campfire. How carefully did you measure out the logs that you used? Did you stop to calculate exactly how much heat would be released by the combustion of that fuel, just to be sure that it would be enough to toast that marshmallow? Or keep your feet nice and toasty on a fall night? Probably not. I know I didn't. But if you wanted more heat, what did you do? Of course, you threw another log onto the fire. Ancient civilizations all knew how to coax energy from wood by burning it, and they all knew that more fuel meant more energy. But the need to quantify exactly how much energy was never really there until the Industrial Revolution came about. In the early 1800s, engineering and manufacturing advancements spurred the development of engines, electrical systems, and other devices requiring very specific amounts of energy be delivered in very specific ways. This new need to understand energy quantitatively drove a curious beer brewer by the name of James Prescott Joule to take on a little research project involving a new invention, the electric motor. Joule sensed an opportunity, noting that this new electric motor technology might be able to replace or outperform the steam engine technology that his brewery used in those days. And he set about studying electrical energy. Joule knew that engines produced two things, heat and work. This is to say that they could impart a temperature change on their surroundings, usually an unwanted side effect, or they could physically move other objects by applying a force, the physical definition of work. Usually, These devices produce a little bit of both. But Joule quickly noticed that there was an intimate relationship between the amount of work a system could do and the amount of heat that it generated. Specifically, the more heat a device produced, the less work it could do per unit of fuel consumed. He observed that this was true regardless of the source of the energy, steam, electrical, or otherwise. Minimizing heat meant a greater amount of work could be done by a device. Joule had made a revolutionary realization. He had realized that all energy is interrelated. Mechanical work and the generation of heat seems to always balance out, meaning that they must be made of the same stuff, all of energy. Even if you aren't aware of his story, you're probably aware of his name, because chemists and physicists have used it to dub the most fundamental unit of energy. In fact, we used it once already in our discussion of light's ability to carry energy. A joule is the amount of kinetic energy imparted to an object when 1 Newton of force acts on it over a 1 meter distance. 1 watt of power applied for 1 second transfers 1 joule of energy also. There are a few other common units of energy, including the calorie. A calorie is equal to 4.17 joules and is the amount of energy needed to heat 1 gram of water by 1 degree centigrade. This is not to be confused with the food calorie, which is 1,000 times greater than a simple calorie. Both of these units are the metric cousins of another well-known unit of energy, the BTU, or British Thermal Unit, which is the amount of heat needed to raise the temperature of a pound of water by 1 degree Fahrenheit. In theory, any one of these units is just as good as another. BTUs are very rarely called upon, though, in modern chemistry. And there are those chemists who choose to work in units of calories, but because of its more fundamental metric system foundations, newtons of force and meters for distance, the joule is by far the preferred unit of energy in chemistry. So we're going to stick with joules for our discussion. The first law of thermodynamics tells us that energy can never be created or destroyed. It can only be exchanged. But exchanged between what? We can't talk about exchange without 2 discrete entities participating in the transfer. So the first order of business in any thermochemical experiment is to define 2 separate entities that do not mix together. First, we define our system, which is usually the reacting matter we want to study. Next, we identify the surroundings, which are technically all other matter in the universe. We can't really ever say the absolute amount of energy contained in any chemical system, but we often can measure how its energy changes when chemical processes take place. So we sometimes place a capital Greek delta in front of terms like energy. The delta is a standard symbol meaning change, so delta E means a change in energy. Energy change is a 2-way street. Energy can flow from surroundings into a system, or from a system into its surroundings. By convention, we always write these terms from the perspective of what we have defined as the system. So if a system is losing energy, we use a negative sign to demonstrate that the system's energy is decreasing. If instead a system is gaining energy, then we use a positive sign to indicate that energy is flowing into our system from the surroundings. But we still haven't answered the simple question: what is energy? To do this, we really need to carefully define the 3 fundamental entities that we discussed previously: energy, heat, and work. We use these 3 terms on an almost daily basis in conversation. And most of us are accustomed to thinking of energy as that invisible force that powers our cars and electrical devices. Heat might conjure thoughts of varying temperatures. And of course, work makes us all think of physical processes like lifting or carrying an object from one place to another. But the language of science is a bit more structured. And if we're going to measure these quantities and rely on Joule's observations, then we have to be able to relate them mathematically. So let's set a firm definition for how these are interrelated before we continue. In short, energy is equal to heat plus work. This is to say that all of the energy in the universe is really only useful for 2 things: warming things up or pushing things around. Now think about a material that we've already considered several times, propane. Propane is a fairly simple molecule with a molecular formula of C3H8. It can be burned in excess oxygen to form carbon dioxide and water, a reaction known as combustion. Now, common experience tells us that combustion of propane releases energy to its surroundings. That energy can be used to produce heat for your home, cook your food, or it can also be harnessed to do mechanical work, like moving a vehicle. Which of the two happens to the greatest extent depends on the design of the device in which the propane is being combusted. But if you were an engineer, wouldn't it be nice to know exactly how much energy is released during this reaction? This way, we know exactly how much heat or exactly how much work can be done when propane is used as a fuel. The easiest way to determine the total amount of energy changing hands during a process is to carry out that process in such a way that no work is done at all. If that can be accomplished, then our equation simplifies. Heat and energy become equivalent. So for the duration of this lecture, we'll be making this very important assumption, that no meaningful work is being done by the reactions we're investigating. This way, we can measure the heat flow in a process to determine the total amount of energy that changes hands. After that, we can hand off our results to the engineers and let them design ways to turn that energy into work instead. So to begin understanding how chemists look at energy, we had to simplify. We have eliminated work completely from our equation. We can do this by assuming that our chemical reaction does no work and takes place under conditions of constant volume. If our container were to expand or contract, then work is being done, and we want to avoid that. When heat is equal to energy in a system performing absolutely no work, we give that heat a very special name. We call it enthalpy. So let's figure out what enthalpy is and how we can measure it, with the understanding that the term heat may also pop up occasionally as a synonym in this special assumption that no work is done. When a chemical reaction takes place, enthalpy almost always changes hands in one way or another. It must either flow out of or into the reacting system. A reaction which releases heat to its surroundings is said to be an exothermic reaction. Conversely, a reaction that absorbs heat from its surroundings would be called endothermic. Endothermic reactions are a bit less common, though no less important than exothermic reactions. But let's focus on an exothermic reaction, like the burning of fossil fuels, which our society relies on so heavily. Just how much energy can a fossil fuel provide when it's combusted? If we devise a system that does no work, we can simply track how heat moves and use that to determine the total energy of a process. And how do we measure heat? Of course, we use temperature. But there is a catch. The temperatures of different substances change differently as they absorb or release similar amounts of heat. Metals, for example, tend to increase in temperature dramatically with the addition of just a small amount of heat. Don't believe me? Just grab that south-facing doorknob on a sunny summer afternoon. Ouch. But other materials, most notably water, need much, much more energy to increase by the same temperature. That same summer sun can beat down on the surface of your swimming pool or your cold beverage all day, and you never have to worry about scalding yourself when you leap in for a dip or take a sip. These materials are said to have different specific heats. A specific heat for a substance is a measure of how much energy is required to heat 1 gram of material by 1 degree centigrade. We sometimes denote this value in equations with a capital S or a lowercase c, so you may see it both ways. Water has a specific heat of 4.18 joules per gram degree centigrade, which means it requires 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree centigrade. In contrast, metals, like copper for example, have much lower specific heats, in many cases 10 times less than that of water. Now, specific heat is what we call an intensive property, which means that it does not change with amount. The specific heat of water is 4.18 joule per gram degree centigrade, no matter how much or how little water you have. But in practical situations, we don't always work with just 1 gram of water. If you place 2 pots of water on the stove, for example, one small and one large, heat them on similar flames, what will happen? Well, of course, the smaller pot will boil first. Its temperature changes more in response to the same amount of heat being added. So we need a second parameter, which is extensive, or depends on the amount. We call this parameter heat capacity for an object, denoted by a capital letter C. Heat capacity is easily calculated if you know the mass of the sample you'll be heating. We simply multiply specific heat times the mass of the material, and voila, we get a value with units of joules per degree centigrade. This allows us to directly correlate temperature change of a certain object to the heat transfer that caused that temperature change. Finally, we're ready to do some calorimetry. So we're finally ready to answer the question, how do chemists actually measure the heat of a reaction? To get our answer, we have to go back to the mid-1800s. It was a French chemist by the name of Pierre-Eugène Marcellin Berthelot. Berthelot was a contemporary of Joule, and just like Joule, the industrial needs of his day drove him to study the storage and release of chemical energy. Far from being interested in beer brewing, however, Berthelot's passion was something that should never be mixed with alcohol: explosives. In an age when manufacturing and construction was booming, someone had to produce the raw materials, and that meant mining, which meant the use of explosives. To that end, Berthelot sought to understand the exchange of energy during explosions. The more he understood this, the better he could make his products. The value in explosives is in their ability to release energy in the form of work. But determining an explosive formulation's potential could be accomplished more easily and much less destructively by measuring the heat it generated when that explosive was detonated in a system that actually prevented it from doing work. In the real world, that's much easier said than done. First of all, in this case, the surroundings are the entire universe except for that small sample of explosive being detonated. How do you measure the temperature of the entire universe? Second, when bombs go off, the matter making them up is thrown about and mixes with the material around it. This would be detrimental because the system and surroundings will have to remain unmixed if we're going to determine how much energy flows between them. But Berthelot solved both of these problems in one ingenious design. He fashioned a device consisting of 2 chambers. The inner chamber was made of thick walls and sealed tightly to contain the explosive reaction that would take place inside. Now, this chamber was so thick that no expansion could possibly take place during the reaction. In other words, no work could be done. The outer chamber was filled with water and insulated from the outside world so that no heat could get into or out of that vessel. Essentially, Berthelot was creating a miniature universe in which his system, his interior chamber containing the reacting explosives, did no work, and the surroundings, the water filling the outer chamber, could absorb essentially all of the energy of the reaction as heat. He named this device a calorimeter. Behold, the entire universe. Okay, not really. But in a thermodynamic sense, I can create a little universe like this, as long as I ensure that heat can't be transferred into or out of it. So I've created a small system here that I've thermally insulated. So this barrier here, let's assume, is completely impervious to heat. It can't get in and it can't get out. If that's true, from a perspective of heat, this really is a tiny little universe. And a universe, of course, consists of 2 basic things: a system as we've defined it, and everything else, which we would call the surroundings. So, how can we use this miniature universe that we've created to conduct experiments about how heat moves and is absorbed and released in reactions? Well, just like this. Let's assume a few things. First, let's assume that the mass of my surroundings is much, much greater than the mass of my system. In other words, that the mass of the universe and the mass of my surroundings are essentially the same. Then let's also assume that the laws of thermodynamics are in place here, and that delta H of our universe is absolutely zero. It can never change. This means that when heat goes out of the system, it must go into the surroundings in a measurable way. Now, if we're going to let these assumptions hold, we can do some really interesting experiments with our miniature universe to discover when and how heat flows during chemical processes. In order to do this, we're going to have to take the temperature of our surroundings. So I placed a thermometer in here. Now, in an actual calorimeter, which is what this device would be called, we'd have some kind of a paddle stirring or agitating to be sure that our system's at thermal equilibrium. So right now, I'm right around room temperature, let's say. Now, I'm going to, for purposes of demonstration, duplicate this setup here, put another thermometer in there. And again, this is right now resting at room temperature. But if my closed system contains some kind of chemical reaction or process going on that releases or absorbs heat, I'm going to see a change in that system. Let's think about an exothermic process. In the case of an exothermic process going on over here inside of the system, it's going to release heat and the system will, of course, correspondingly heat up. But we also know that heat likes to distribute itself. And so, over a little bit of time, that heat will make its way out into the surroundings and therefore heat up those surroundings. And sure enough, you'll notice that the temperature has actually gone up somewhat. Now, it's this change in temperature that's going to give me some information about how much heat was exchanged between my system and surroundings. I could do a similar experiment with an endothermic process. If instead we have an endothermic process occurring inside of our system, that's going to get cold. And what will that do? Well, that's going to draw heat in from the surroundings, causing the temperature of the surroundings themselves to go down. Again, I should observe a change in temperature. Now, we use this change in temperature in order to calculate how much heat moved, because the laws of thermodynamics tell us that if we know how much heat moved, we know how much heat must have been absorbed or released in the system. Q, of course, represents the heat that's gained by the surroundings in this case. Next is M, the mass of the surroundings, which we multiply by C, the specific heat of the material that makes up the surroundings, in this case, water. And of course, M times C gives us what we call the heat capacity of the calorimeter. Finally, we include our data, delta T, the observed change in temperature. This allows us to calculate how much heat the surroundings have gained. So, how is that useful to us? Well, knowing how much heat the surroundings gained tells us exactly how much heat the system lost, or vice versa. Knowing how much heat the surroundings have lost tells us how much the system gained. And we do that using, again, a calorimeter. Let's do a real experiment. Here is an insulated water bath. That's my universe. I'm going to make the water bath my surroundings by placing about 10 kilograms of water into it, and then placing in a small container. And that small closed container will be my system. Now, we've been working a lot with the combustion of propane, so let's continue to do that. Let's put some propane inside that container. Specifically, I'm going to put exactly 10 grams plus enough oxygen to ensure total combustion. And we know how to do that because we already understand how to use stoichiometry. So we can be sure that there's excess oxygen and that propane is my limiting reagent. I mark my initial temperature and then combust my sample. What happens here, of course, is heat's released. So immediately, the system itself is going to heat up. But very quickly, that heat will be transferred into the surroundings. And as it does so, again, I expect to see a temperature change. And sure enough, here it goes. By comparing the final and initial temperatures of my calorimeter, I can determine exactly how much heat changed hands. 12.2 degrees centigrade in this case is my measured temperature change. So, using the equation that we discussed just a moment ago, Q equals mc delta T, I can determine that the amount of heat that changed hands in this reaction is equal to the mass of my surroundings, because that's what I was measuring the temperature of, the specific heat of my surroundings, which in this case is water, and water has a specific heat of 4.18 joules per gram degree centigrade, and finally, my observed change in temperature, 12.2 degrees centigrade. This will tell me the total amount of energy that moved when the heat was transferred from system to surroundings. Do my unit analysis just to be sure that I've got my equation right, And sure enough, it's going to give me units of joules, 510,000 of them, which is a bit easier to think of as being 510 kilojoules. Now that tells me how much heat in this specific example exchanged. But I would like a quantity that I can apply to any amount of propane that I want to. So I want to get this number adjusted for the quantity of reagent that I used. In this case, I used 10 grams of propane, which I'm going to estimate has a molar mass of 44.1 grams per mole. Notice I put it into my equation down here using the proper orientation so my units cancel. Right? So I'm dividing through by that molar mass to get moles of propane. And this is our standardizing number here. So I want to know how many kilojoules a mole of propane will produce. And to do that, I simply divide the heat that was transferred in my experiment by the number of moles that I used in my experiment. This would give us 2,247 kilojoules per mole. This is the molar enthalpy of combustion for propane. Berthelot's invention was originally designed to measure heat being exchanged in powerful, violent chemical reactions, the likes of which you would never want to encounter in your kitchen. But with a few slight modifications, you can recreate a simpler version of his famous device right at home and even measure delta H for a few less potent chemical processes. Welcome back to the kitchen. Now, we can't do a calorimetry experiment like Berthelot did, because that would involve using combustible materials and generating an awful lot of heat. But there is another type of calorimetry experiment that's very similar. We can measure what we call the heats of solution of certain salts. And I'm going to show you how you can do that at home right now. Now, to do that, you're going to need a relatively accurate thermometer. I like to use digital thermometers like this one that have a thermocouple probe and that read to at least the tenths of a degree. I've also got a sample of potassium chloride, which is the base that's used in many salt substitutes. And I'd like to determine exactly how much heat is released or absorbed when a given amount of potassium chloride dissolves into water. So I'm going to do this using what is essentially a coffee cup, and we sometimes call this a coffee cup calorimeter. But I've purchased a little self-stirring cup here. Now this way I can leave the lid on top while I activate the blade and stir what's inside. That's going to be critical because I want to be sure that everything is of a uniform temperature at the end of my experiment. So let me place that cup on one of my balances, which I'm going to activate. And just to be sure that I've got a very accurate reading here, I'm going to re-tare my balance, even though it reads 0 already. And I'm going to add to that a certain amount of water. Now, the water is going to be behaving as my surroundings. Remember, a calorimeter is a miniature universe. So we'll have a system and surroundings both contained within the calorimeter. Let's get a little more on there. Okay. So it looks like I've added 373 grams of water to my calorimeter. In other words, a 373 gram sample of surroundings added to my universe. Now, my next step is to determine what the heat capacity of my calorimeter surroundings are. So I simply use the specific heat of water and the mass that I've measured here. I can determine that I have a calorimeter with a 1,561 joule per degree centigrade heat capacity. And I'm going to use that to determine exactly how much heat is absorbed or released when a sample of my potassium chloride is dissolved. Well, to do that, I'll need to know the mass of potassium chloride that I'm using as well. So I've got a second balance here, and I'll start that up and be sure that it's properly tared. And I'll add my sample of potassium chloride so that I can get an accurate mass. Looks like I have 37.9 grams of potassium chloride, just about a half of a mole. Now, I need to begin my experiment by first measuring the initial temperature of my calorimeter. Then I'll add and dissolve my potassium chloride and remeasure the temperature in the calorimeter. Using the specific heat of my calorimeter and the number of moles of sample dissolved, I can calculate the molar enthalpy of dissolution of potassium chloride. So now that I've collected my mass data, I really don't need my balances anymore. So I'm going to move those out of the way. And measure the temperature of my calorimeter before adding my sample. So I've given myself a little opening here so that I can insert my thermometer. And then I can verify the temperature of my calorimeter this way. So it looks like the initial temperature of my calorimeter is 69.2 degrees. I want to make a note of that so that I can determine how the temperature changes with the addition of my solute. Now let me remove my thermometer here so that I can get access to my calorimeter. And I'm going to add my solute, close my calorimeter, replace the thermometer, and stir until I have it completely dissolved. So here we go. And this is where battery power is a wonderful thing. I can simply start up my cup and just allow that stirring to continue until it's totally mixed. And as that stirring progresses and we begin dissolving potassium chloride, there should be an obvious change taking place on the thermometer. So as you can see, the temperature has dropped precipitously as the potassium chloride dissolved. That means that heat is being absorbed as the potassium chloride is dissolving into solution. In fact, solution is becoming nice and clear here. It looks like we're about done. So let's let that stirring stop to be sure. And sure enough, looks like we've dissolved all of our salt. And our final temperature, 59.7 degrees. Now I'm ready to calculate my change in temperature and determine exactly how much heat 1 mole of potassium chloride absorbs when it's dissolved in water. So assuming that no work was done, and that my calorimeter was absolutely and completely insulated from the outside world, I can take the temperature change of the water, calculate the heat required to cause that temperature change, and assume that all the heat that was released or absorbed by the reaction inside is accounted for. At the very least, we just devised a new method to test your salt to see if it's low sodium or not. So let's review what we've covered in this lecture. We started by classifying the terms energy, heat, and work. And we saw that heat and work combine to account for the entire amount of energy in any given system. We talked about how energy can be thought of as flowing between two separate entities, a system and that system's surroundings, remembering that we report changes from the perspective of the system. We discussed how chemists measure the energy changes in reactions by trying to consider systems which are doing no work, thus making heat equal to energy, and how we can use a special term, enthalpy, to describe heat when work is not being done. We talked about specific heats, which are a measure of how easily different materials can be heated, and about heat capacities for objects, which account for their mass and allow us to directly relate temperature changes in those objects to the amount of heat that they absorb or release. Then we took a look at the calorimeter, one of the tools of thermochemistry. We saw how isolating a reaction in a small insulated space allows us to create a miniature universe called a calorimeter, and how the first law of thermodynamics allows us to measure the heat released or absorbed when a reaction takes place. But we aren't done yet with our discussion of thermochemistry. Next time, we'll learn about a very special rule that often allows us to bypass the calorimeter and estimate heats of reaction using little more than a pen, paper, and our expertise in thermochemistry.